So, a little more involved because, well, you tell me, why? Why is this more involved in what we've been doing? Because distance, initial velocity, what is that? What chapter is this? Stuff. Kinematics. Now we have dynamics with kinematics. How far up the slide does it go? I'm trying to find D. I have an initial speed of 6. What else do I know as far as the kinematics go? Do I know A? I know gravity's 9.8. Problem is, the penguin isn't flying straight out of the ocean. He's flying out at an angle, and he's landing on this ice slide, which has friction. But if I'm trying to calculate, remember our bottle rockets, if I want to know how high it goes, what else do I know? At the top, yeah, that's when he gets to 0, well then he's going to start sliding back down because of gravity. So I know the final velocity is going to be 0. This is what I need to find out. Acceleration. If I have acceleration, I'm done. Okay? Because there's a formula that relates this, isn't there? Okay, I know that. I know that. I need to find that. So if I know my piece of my puzzle here, A, I'm good. Is there acceleration in dynamics? You bet there is. So how do I find acceleration? Well, we analyze this guy in the perpendicular and the parallel directions, i.e. a force-body diagram tells us this guy, this little guy has mg, and perpendicular to that, we have this component. Parallel, we have this component. Okay, we have, so I can just squeeze her in there, normal force. What are the forces on this thing? I got it. Ah, what direction is the force of friction? Always opposes the motion, right? So far we've seen a lot of this going on because you know the block's going to go this way. That's the tricky part here. It's in the opposite direction, isn't it? So force of friction is always opposing the motion. This guy is going that way. Should have wrote that up here somewhere. Look a little cluttered, okay? So that's got to go that way. And then just like in our lab, which was actually not moving, static equilibrium, but this is why we want to do free body diagram. We analyze the forces, okay? And if there's a net force, then you take the difference of the two forces. If there is no net force, is this guy moving in the perpendicular direction? Then they got to be equal, all the arrows. Okay, so perpendicular, I know Fn is equal to this component here, which is, which component's that? That's some angle 35, it's also there. That is not opposite, that is cosine. Okay, that's all that's going on in the perpendicular to my ice slide, perpendicular direction. In the parallel direction, that means parallel, what's going on? Here is the formula, but we want to apply that to the concept. Okay, the net force, MA, is the unbalanced forces. This thing's moving, there's an acceleration, it's got to be an unbalanced force. So I have this going that way, I also have that going that way. This component is mg sine theta, that's opposite to this 35-degree angle, which is the same as this one. And that's in the same direction as this, force of friction. Okay? So force of friction, we know that as a formula. That's mu Fn. And Fn is mg cosine theta. So force of friction is mu mg cosine theta. So let's throw that down in here. Ma is mg sine, let's put the angle in, 35, and mu 0.1 mg cosine 35. What's the formula? It's not the formula, it's the concept, okay? Formula is just Newton's second law. You have to know to get from here to here. Okay? Every question might be a little bit different. You can't memorize 7 formulas. You have to take this formula and apply the concept. That's why we need a good free body diagram. In case you didn't know already. Everybody okay with that? Now, what can I cancel out here? Well, not quite mg, but yeah, the little mass of this little penguin guy doesn't matter. And A is g, well, let's not even, we know it's 9.8, right? G sine 35 and 0.1 times g cosine 35, that's just nothing but numbers, isn't it? So feel free to put that in each question. It's in the question. It's a 2-kilogram penguin, but you know, why bother? Okay, so, and I could factor out 9.8 if I really wanted to impress someone. Oh, gotta put that in degrees. 9.8 sine 35, close the bracket, plus 1/10 of 9.8 times cosine 35 is 6.4. Seem reasonable? Are we expecting something less than 9.8? Well, it depends how fast you came out of the water, I guess, right? Looks good to me. Meters a second squared, that's my acceleration. So, I didn't answer the question. How far up the slide? Well, the final velocity is 0, the initial is 6, and 2. Now, what direction is this? Yeah, because remember, he's slowing down, right? That acceleration is in this direction. You have to put the sign in here. Okay, so 36 over 2 negative 6.4 will give me how far he goes up the slide. That's 18. And 2.8. Yeah. But, yeah, okay, that's fine. Nice. And well, I didn't even put the minuses in here. In this case, it doesn't really affect the answer, does it? Okay? D positive, D negative, doesn't really matter. But I just want to point that out anyway. 2.8 meters. Seem reasonable? Okay, if I got 642 meters, might not think that kind of makes sense. Usually the questions will. That's how far up he goes up the slide. So, mixture of kinematics and dynamics. Okay, you know accelerations in both chapters. Add You've already done 1, 2, 4, 5, 11, 15, 18. Number 3 is going to look a lot like your lab you did last day. 3, 6 to 10, 12 to 14, 16, 17. So that'll be all of them up to 18. And they got a new example tomorrow, and this, it's pulleys actually. Okay, blocks on attached with ropes, which we call tension, and pulleys. But you need another example for those, I would think. Okay, so today and tomorrow we should be done this sheet, and then we'll see where we go after that.